Okay. Okay. So I forgot to start the recording. So let's say that we are discussing about the Maxwell equations. We already commented the two first equations, the Gauss theorem and the analogous for the B field. There is a third equation that is the curl of the electric field. In Italian, this would have been written rotation of the electric field. In English, it is curl. Of the electric field is minus the derivative respect to time of the B field. This is the so-called Faraday-Neumann-Lenz law. So a time-dependent B field can induce an electric field that has got a curl that is different from zero. And this is the basics of electrical transformers, of the low-frequency electrodynamics, all what is the application in electrical engineering. The fourth equation is the so-called Maxwell-Ampere equation. Before Maxwell, this was the Ampere theorem that tells you that if you calculate the integral of the magnetic field on a closed loop, this is always equal to the current that is passing through the loop in static conditions. So curl of H is equal to J. J is the current density. If you have time-dependent fields, you have to add an extra term. This is the derivative of the D field with respect to time. And this was added by Maxwell. Now, these are therefore called the Maxwell equations. This is end of the 19th century, 1875. Please keep in mind that Maxwell writes these equations in 1875. And in 1883, Hertz generates the first artificial electromagnetic wave. And 2 years later, Marconi builds the radio. So in 10 years, we pass from a paper published in the Royal Transactions in England, in 10 years, from a theoretical paper to the radio, the application. So this is the normal time scale that you should keep in mind. It takes 10 years to pass from a theoretical discovery to its application on the market. Okay? Now, these four equations are complemented by the so-called constitutive relations. These constitutive relations, as you see in the Maxwell equations, you have four fields: the electric field E, the electric displacement D, the magnetic field H, and the magnetic induction B. Okay? And here, the constitutive equations are equations that are relating the relevant fields, D, E, B, and H, to the matter in which your electromagnetic wave is propagating. We know that when an electromagnetic wave is propagating inside a medium, you have an electric field associated to the electromagnetic wave and the magnetic field. These fields will make that the medium in which you are propagating, water, air, glass, semiconductors, whatever, the medium is reacting because charges are displaced by the fields. And therefore, when you have light propagating in a medium, you can induce a polarization of the medium, P. That means that the charges can separate and you can induce electric dipole inside the medium. And you can induce a magnetization of the medium, M. That means you can induce magnetic dipoles inside the medium. Okay? Now, there is a relation that is relating the vector D, this is the first one, the vector D, the vector E, and the vector P, that D is epsilon naught times the electric field plus the polarization. It might be that foreigner students saw these equations not in the International System of Units. These are written in the International System of Units. It may be that they saw these equations in the CGS system. For example, in Russia, they use such a system. And therefore, this constitutive relation would be a bit different. You would have a speed of light appearing in this. But we use this notation here. And the B field is mu naught. Mi is the magnetic permeability of vacuum. Epsilon naught is the electric permittivity of vacuum times the sum of the magnetic field plus the magnetization. Okay? Now, generally, when you have an electromagnetic field propagating in the medium, generally, the polarization that you induce in the medium is a function of the electric field. And this function is a vectorial function and can be very difficult to describe physically. So in general, there is no simple model that is relating the electric field that you get in the medium and the polarization that you induce. The dependency can be very difficult to describe. And the same is for the dependency between the magnetic field and the demagnetization. Okay? Now, you, in your general physics courses, you have only one example that shows you what is the difficulty of relating the field to the magnetization. And this is when you studied the ferromagnetic materials. You remember that when you studied ferromagnetics, you find out that the magnetization has a graph with respect to the magnetic field that shows an hysteresis. You remember? And you discussed that the magnetization that you have in a magnet is not only depending on the magnetic field that you have at that time in the magnet, but also on the history. That means on how you apply the magnetic field in precedent times. There is an hysteresis behavior, okay? So, and this is the same in the electric field, but it is more rare to find it out. And therefore, in the general physics courses, it is not described much, okay? Maybe the only example where you have a similar phenomenon to hysteresis in the electric field side is the behavior of liquid crystals, okay? Now, generally, all ferromagnetic materials that we know, they are out of iron, cobalt, titanium. They are not transparent to electromagnetic radiation. Electromagnetic radiation is strongly absorbed in these materials. So generally, we never study propagation of light in ferromagnetic materials, okay? And so we can rule out the case in which we have ferromagnets. This makes that you can say that generally the material in which you propagate light is either diamagnetic or paramagnetic, okay? And normally diamagnets and paramagnets are very weak magnetic materials. The magnetic response is very weak. And therefore, you can directly say that since the magnetization is weak, you can write it as a constant, the so-called magnetic susceptibility times the magnetic field H. And this is the assumption that we make. Now, it might be that you have difficulties in reminding how these equations were derived. We don't mind about that. This is not matter of this course. This is just to say that Maxwell, in 1875, adds this term to the fourth equation, and then by working on these equations all together, he finds out the so-called wave equation. Okay, so he finds out that the electric field that is associated to a perturbation must satisfy a wave equation that is similar to the equation for the vibrating chord, okay, that was discovered by D'Alembert. So must satisfy this equation that is written here. And in this equation, you have that the so-called Laplace operator that is acting on the electric field minus the product of the two constants of the let's say the domain of electric field and the domain of magnetic field, okay, times the second derivative of the field with respect to time must be equal to B naught, the second derivative of the polarization with respect to time twice. Okay? Please keep in mind that until Maxwell, the two communities of people working on the electric field and working on magnetic field were separated. These were physicists participating to different congresses, teaching in different courses. Okay? Only Faraday had somehow given an indication that there should be a connection, but the connection was still weak. At that time, the dielectric constant epsilon naught of vacuum was measured by Faraday. The magnetic permittivity of vacuum, μ naught, was measured by Henry, and they had measured with several experiments. Okay, and there was no relation. Okay, it is as if today I would say to you that an engineering studying in this faculty should deal with somebody working in psychology of the dogs. As if I would come in this room and would say, you look, you should speak with people dealing with psychology of dogs because there are some things that are common to your fields. What would you say? There's nothing in common, but maybe there is. So keep this in mind. Now, why Maxwell did this? Because Maxwell was born at let's say mid of the 19th century. He was a student in Oxford, okay? And you know that when you became a student in Oxford, there was this tradition that every student, every, let's say, brilliant student had a tutor. And the tutor was a professor who was taking care of his preparation, okay? It was so strong, this system, that there was a competition at the end of the year where students competed among themselves to become the best student in mathematics, okay? And this competition among students was, as a matter of fact, a competition among professors. Everybody was preparing his pupil, and everybody was making that his pupil was the strongest. And the educators of Maxwell, they were professors in mechanics of vibrations. So Maxwell was a student who had studied morning, day, and night mechanics of vibrations, D'Alembert law. So he wanted to demonstrate the light was a wave. Okay, so when he had this term here and he worked out this equation here, he found out that this equation was very much similar to the D'Alembert equation and wrote this in this simple form. Now we go to the next slide. What does it happen if you think that you are in vacuum If you are in vacuum, then vacuum, there has no matter, there is no polarization in vacuum. So the term that was on the right-hand side of this equation is 0. The Maxwell, the propagation equation becomes exactly the same as the D'Alembert law. Then you discover that this term here can be related to a speed of propagation. And Maxwell takes the value of epsilon naught and the value of mu naught, calculates the product, the square root and the inverse, and finds out that this was the same value that Fizeau, Foucault, and others were measuring for the speed of light in vacuum. So he demonstrates that this epsilon naught and mu naught are related to the speed of light. At a glance, at that moment, the communities of people working in magnetism and electric field merge together with a community of opticians, and you have a new research field. And this new research field will push Marconi to build the radio and will be the engine pushing technology until the discovery of quantum mechanics. So keep in mind that the next 30 years after Maxwell will see people working only in electromagnetism. Waves, 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 and waves. Okay, that's clear to you? Now, this is what happens. Now, we go for a while back here to this equation that you see on the screen. And this is not, of course, let's say, it might be that you have difficulties in fully understanding this equation, but there's one thing that is clear to us after our courses of basic physics. When you see a differential equation like this, okay, you have the derivative of the electric field with respect to space, the derivative of the electric field with respect to time. So this is a partial differential equation. That's clear to us. When you have a partial differential equation and you have a term here that is not depending on the field, then you call it a non-homogeneous partial differential equation, okay? If you are in vacuum, the equation becomes homogeneous. There is no driving term. If you have the equation like this, there is a driving term. And now this is, I mean, we don't go deep in details, but we have something to understand. When you have a mechanical oscillator, okay, that is driven by a force, let's say a dad who is at the park with his daughter, she is on a, how is called? On a swing, the daughter is sitting on a swing and the dad is pushing, okay? So the daughter is a mechanical oscillator, the dad is the forcing force. When you write the equation for this system, you have the equation of the mechanical oscillator and the effect of the force is on the right-hand side here, okay? So the so-called driving term. Now, what does it tell you, this equation in general? It tells you something like this. When you have an electromagnetic wave, this has an electric field associated, E. If this electromagnetic wave gets inside a medium, now what does it happen? The electromagnetic wave gets inside the medium, the electric field will displace charges. So the charges in the medium will be separated, and this will make that locally you will have a polarization. So the medium will polarize, okay? But now, what does it happen if you have a dipole in in space. Think, for example, to an antenna, the antenna of your cellular phone. When you have a dipole that is oscillating, this dipole will generate electric field. Okay? So as a matter of fact, what is happening? If a wave is getting inside a medium, it is exciting the medium. Part of the energy of the wave, the electromagnetic wave, will become kinetic energy of the charges. The charges will move. Since they move and oscillate, they will radiate field. And this field that is radiated will be superimposed to the original field. So you have a wave that is exciting the medium that is generating a wave, the wave that is exciting the medium. It is an interplay between the wave and the medium, a continuous interplay. Okay? And it is written here. It is written here. The equation is driven by the depolarization that the field itself is inducing in the medium. Okay? Now, to make it simple, not to, let's say, push students to desperation and suicide, no? In the basic physics courses, generally your professor is saying, okay, but in a very simple approximation, the polarization in the medium is proportional to the electric field. So you make a linear model. You say P is epsilon naught times the electric susceptibility times the electric field. So as a matter of fact, what you are doing, you are saying, okay, this relation between the polarization is the field is very complicated. But in a first order approximation, I take the first Taylor term and I say P is proportional to E. Of course, it is an approximation. And this is what you call linear optics, what you do in linear optics or in basic optics. Okay? So normally, you say that P is proportional to the electric field times a constant that, due to the fact that we are in the international system of units, is epsilon naught times chi. Okay? Now, be careful, because in this writing here, you also assume that the medium is isotropic. What does it mean? That if you apply the field along one direction, the polarization will be along that direction. The two vectors are parallel to each other. But this is not really the simplest case. This is the simplest case, but it is not the most general case in general. Okay? If you drive the bicycle, or if you drive the motorbike in Roma, you know that if you are going along the road where there is a tram line, and there are the tram, you know that when you cross the tram line, you should try to cross them transversely. Because if you go parallel to the tram line, they will trap you, your wheel, you will go with your bike inside the tram, and you will make a crash. Okay? You have to cross like this, because that is an anisotropy of the road. There is a preferential direction, and that means that it will push you along one direction. If you have a tram on that line, if you apply a force transversely to the tram, you will not displace this, because it can go only in that direction. But if you push the tram along the lines, and you have many people, you can push it along. So we will go back to this. So in general, in an isotropic medium, in linear condition, you do this assumption. And what does it happen if you make this assumption? In the wave equation, it happens that the driving term that is here, that is the second derivative of P with respect to time twice, if here here in P, you replace the linear expression, then you can work out something like this. Then you can shift this term on the left-hand side of the equation. If you shift on the left-hand side, you can factorize the second derivative of the field with respect to time. It appears a prefactor that is 1 plus chi, 1 plus the susceptibility. And as usual, when you have a new quantity and you are an engineer, you give to this quantity a name, okay? That is epsilon r, the relative dielectric constant. So you work out this and you say, okay, now if I do this, I have again the D'Alembert equation that I know, but the prefactor is not anymore mu naught epsilon naught, but there is an extra factor that is epsilon r. That means that when you calculate the speed, this is 1 over the square root of epsilon naught, epsilon r mu naught. You are assuming, you are separating here. The first term is the speed of light in vacuum, what we defined before. And the speed of light in a medium is the speed of light in vacuum divided by the square root of the relative dielectric constant that you call the refractive index. Okay? So you find out that the speed of light in a medium is smaller than the speed of light in vacuum by a factor that is the refractive index. Okay? Now, this factor, the refractive index, is the square root of epsilon r, that is the square root of 1 plus chi. Okay? So, if chi is large, the dielectric constant epsilon r is large, the refractive index is large, the speed of propagation is low. The wave is slowed down. Okay? Now, and this is important for me to point out, at this stage, maybe that you do not understand why I am telling you these things, but then we will go back to this. Now, in the frame of this view that I gave you, what is qualitatively happening? I have a wave coming with the speed of light c from in vacuum. I'm arriving, okay, with the speed of light. You get inside a medium. What does it happen? It happens that the energy of the wave is given to the medium because you take the charges and make them oscillate, okay? So part of your energy is going to these charges, okay? These charges are radiating again the electric field, okay? This electric field that is irradiated is summed up to the original field. So you give and receive, give and receive. Now, you know that in physics, there is a quantity that is called the mass of the electrons. And the mass, when you hear mass, you say, there is inertia. There is a delay. So when you put energy in the charges will keep for some time this energy and then give you back. So there will be a delay with which the energy is given back. And what does it happen when you sum up two oscillating functions? Think, for example, to two sinusoids. One that is oscillating plus one that's irradiated back, but that is delayed. These are two out-of-phase sinusoids. And when you sum up two out-of-phase sinusoid, you get a sinusoid that is delayed. So that means that your speed of propagation is lower down. Your energy is being transferred with the lower energy because you have a delay due to the fact that the medium is delaying you. And of course, the most the medium is polarizable, the most is polarizable, the more it is polarizable, the more it will be the delay. Okay, and it is written exactly in these equations that we wrote here. Okay, now in general physics courses, you just cite some facts, but you do not go deep in this. The first fact that you cite is that, in general, the relation between the polarization and the electric field, it is a tensorial relation. What does it mean? That in general, it could be that you apply the electric field along a direction, but the polarization is used along a different direction. So in general, you cannot write that the direction of the polarization is the same as the direction of the electric field. And in general, this term here, that normally in a general physics course, we assume to be a scalar, a simple scalar quantity. In general, chi is a tensor. So in the 3D space, it is a 3 by 3 matrix, is a rank 2 tensor. Okay, what does it mean? It means that if you have a field with a component along X, for example, this can induce polarization which has got components along X, Y, and Z. Okay, so the susceptibility is a rank 2 tensor. That's to say, in our simple approach, a 3 by 3 matrix. Okay. The second thing that you just cite in general physics courses is that this tensor chi is not even real, but it can be a complex quantity with the real and imaginary parts. And this makes that, sorry, I was discussing about the third, let's say, the third fact that you cite is that this chi can be a complex. And this makes that the refractive index, in general, is not a real quantity, but it is a complex quantity, which has got a real part, that is the part what we are acquainted to deal with normally, plus an imaginary part, Greek kappa, that is named the extinction coefficient. So in general, we have that. The second fact that we discuss in basic physics is that the dielectric susceptibility is not a constant in frequency, but it depends on frequency, and therefore the dielectric constant is generally depending on frequency. That makes that the refractive index of the media are depending on the frequency of the radiation that you are sending in this medium. Okay, and this effect is named dispersion of the refractive index. Now, these are the results that normally you have at the end of a general physics course, and that you assume in the optics courses. In the optics courses, you assume that that is true. Okay. Now, in the next lectures, not today, we will go back to this, and we will explain a bit better what does it mean that the medium is anisotropic, what does it mean that there is a dispersion of the refractive index, what does it mean that the refractive index is complex. So the 3 points that we summarized here will be discussed more in detail during the next lecture. Okay? For today, we go back to the Maxwell equation to the wave equation in vacuum, we restrict our description to vacuum, and we discuss some basic properties of electromagnetic waves in vacuum. Okay, just to resume, so I want to introduce you the wavelength, the K vector, the frequency, the polarization, and whatever. So we make a small, short summary of basic optics. Okay. And starting from the next lecture, we continue with the slide and go a bit more in detail. Okay? Now, what time is it? 10:11. Say that we have a quarter of an hour stop, that you relax, and then we start again at, say, at 10:25. Okay? Are there questions? We just this. Sorry.
There are a lot of questions because it's so complicated.
No.
We must wait.
Okay.
Next session.
But hope that the two first slides are okay with you. So, but if you have questions, please ask me and we discuss it. Okay. Now, before we stop, I just say you that I use a book in optics. The name is Lect, and I have the PDF, but I cannot give you, and I will not give you officially. So if one of you comes to me with a USB stick, maybe that I am wrong and please go there. Okay.